ろしいでしょうか。では最後のセッションを始めます。私のコンサルであるの、マット・ドブソン、エンジニアですね。バリバリのエンジニアで、デッドボイトの方に我々のラボ的なチームがいるんですけど、そちらから来て、今これは我々どちらかというと製品とは関係なくですね、オープンソースのプロジェクトを進めている IoT のドットコムがあるんですけども、GitHub とかで皆さんご自由に見ていただけますし、コントリビュートしていくことができるようなもの、それの紹介とデモをしていただいております。で英語なので、もちろん英語が堪能な方はどんどん質問していただいたりしてもいいですけれども、もし聞きたいことがあったりして、うまく聞けるなというときはですね、この後懇親会も彼に残ってもらうので、懇親会の時に言っていただければ、我々も手伝って、お話ししたりすることもできますので、はい、そういう形でお願いします。じゃあ、開始したいと思います。
Good evening, everybody. Matt Dobson, software engineer at Apigee. I'm based out of Detroit, Michigan, and for the past year, I have been researching and building, along with the rest of my team, an API-first platform for the Internet of Things. So just a quick overview of the talk. I'm going to start with a brief introduction to the Internet of Things, and this is more specialized to how we broke the individual problem sets down and applied that research to actually building Zetta and making a solution that was robust and something that people could use to build large systems. Then I'll do an introduction to Zetta itself. I'm going to talk about the platform, what we built it on. I'm going to talk about the architecture, what an ideal setup or deployment would look like when building something with Zetta, and then a couple of interesting features that I think are pretty cool. And then I actually have a pretty cool demo to show off where we're going to control a robot arm in Detroit, Michigan. So let's get into it. So basic intro to the Internet of Things. We like to view it as just a growing, ubiquitous network of devices, seen and unseen. We don't know what they could be in the future or what they are even now, but they're everywhere, and people are constantly working on it, building new things. We kind of determined that devices fall into one of two camps, sensors and actuators. Sensors simply sense the world around you, so moisture, air pressure, temperature, humidity, dozens. And they report that data back to you. You collect it and analyze it. Actuators typically will act on the world around you. It could be a light bulb, a motor, car, really anything that will create change in an environment and hopefully give feedback. Not always, but hopefully. So some issues with the Internet of Things that we've kind of found out after building a lot of stuff over the past couple months. The first big one is interfaces and protocols. There are dozens upon dozens upon dozens of protocols meant for communicating with constrained devices. And most people are still trying to figure out what are the best cases for using each. And we've kind of found out that using those protocols closer to the device and making sure that you don't have a cloud server deployed that could be talking to constrained devices is probably the best approach. And I'll show that off later when we look at Zetta's architecture. There's also tons of new protocols coming out. So how do you take a new protocol that has just been released with new hardware and integrate that into your system if it fits your needs better? Right now, there isn't really a good way to do that. And obviously, the big question of security. How do you secure everything? How do you secure messages? How do you physically secure something? A lot of security issues that aren't in normal software that are in the Internet of Things. Next are devices in large systems. I'm sure we've all heard the numbers, upwards of 22 billion devices deployed out there by 2020. How do we start coordinating these devices in large systems closer to the edge of the network? How can we make sure that a moisture sensor or a flood sensor can detect a flood and then display on signage that maybe you should be taking an alternate route when driving home? And how do we improve upon these emergent behaviors in large systems? How do we take stuff we've learned and stuff we've applied with machine learning and actually improve and give feedback into the system at large scale? obviously the big data question. So, what do we store with data? What do we hold on to? What do we use? What can actually be used with all the data that we collect? We're going to have a lot of sensors out there, and storage will start to really rack up over time. And how do we actually learn from all this data that we've collected over time? And the last one is something that I'm particularly passionate about, is the quality of tooling. How do we build really good tools for people building products? Many tools right now are kind of varying quality. Everything from command line applications, Java applets, or really full-featured IDEs that allow you to debug the microcontroller at a very granular level. And soon, we think that there will be a shortage of developers that have the particular expertise in building things for the Internet of Things, developers that know a lot of C and C++, but we do have a lot of developers who are web developers, who know technologies with scripting languages that are great for building web APIs. And we want to figure out a way that those people can actually start developing these systems alongside all the people that have the particular knowledge already, and apply all of that knowledge, collective knowledge gained over the past decade of web APIs to the Internet of Things. So after all of this research, we came together and we started building Zetta. And Zetta is an open source platform for the Internet of Things. Everything is completely open. It harnesses JavaScript to make development more agile. You're able to apply things you've learned about JavaScript to IoT. And Zetta tackles all of these problems in an elegant and efficient way. So the first problem, interfaces and protocols. We go with a mediation pattern. So Zetta is really lightweight and meant to run in multiple places. And typically, it's first run on a hardware hub, a small embeddable computer into a product, say like a refrigerator, a router, or even a TV that can run Node.js. And then that piece of hardware will mediate protocols. All those protocols that are really good at talking to devices close by or setting up mesh networks, or just being, talking to a constrained device, we mediate those close to the device so we don't have to worry about running all of those things in a data center. So on the other side of that, every device gets an API. Every device gets an HTTP API that's defined by a device definition in Node.js. Devices in large systems. So we've been building ways to actually coordinate devices closer and closer to the edge on these smart gateways. So you can have an app that is stateless that will say, when moisture sensor gets to this threshold, we know there's a flood, trigger signage, and pull data from somewhere else over API to give an alternate route or suggest an alternate route. And we've been expanding this whole notion of apps to around the globe. So now we can actually query for devices in different deployment areas around the world. So we can query for the moisture sensor in Tokyo to trigger off an alert in Detroit. And that's some pretty powerful stuff. Quality of tooling, like I said, this is something I'm pretty passionate about. We've designed everything with the developer in mind. People building products need to love their tools. It shouldn't be a pain or a hassle to get things done. You should be really productive, and you should love what you're doing. And we've also created multiple tools to actually help quickly. So it's not just an API platform where you're writing code. We've also done things like build an API console that makes it really easy to build IoT APIs specifically. And the last one is data. So we allow broadcasting of data over WebSockets, so you can subscribe and in real time pull sensor values and store them anywhere you would like. And that just makes collection and analysis easy. We also display these sensor values in the API response. So if you need them at a slower pace or a pace where you want to control when you get stuff, you don't need to use the fire hose. You can just request it against the API and it will be there. So an intro to our tech stack, what we built Zetta with, our tools to build the product for people building products. So our stack is actually completely Node.js based. And we did that for a couple reasons. Next, it's open source. So everything we've ever done to write pieces of Zetta, so device definitions, the core platform, any kind of prototyping, we've made sure is open source and MIT licensed, so people can learn the same lessons that we've learned and start actively collaborating with us. And like I mentioned before, we've actually built an out-of-box API client, API console that makes consuming this API easier, and I'll demo that towards the end of the presentation. So the next big question we usually get is why Node.js? Why the server-side JavaScript platform? And the first big reason is it's evented and it's asynchronous. So for the Internet of Things, there are devices that come online, go offline, change state, and this all happens within the context of the device. And what Node.js allows us to do easily is set up an evented way of interpreting these events going down to the device and coming back up to the device. And it just makes the problem 10 times easier. It's completely open source, so not only can you read all the code for our platform, you can read all the code for Node.js. You can go look it up, read through the source, and it's all there. And that's something that's really important to us, transparency all the way down. We've also figured that every developer knows some JavaScript, whether they want to or not. It's the ubiquitous language of the web. You just need to open a web browser and you can start writing JavaScript. And that's something that we think will definitely open up the pool of developers to include more people and include more collaboration when creating these systems. And the really awesome thing is it's cross-platform. So it can run on many different platforms. Windows, Mac, Linux, and even some embedded platforms are actually including support for JavaScript and specifically Node.js, which is something that we think is going to be really powerful going into the future. Sometimes we get asked why open source. I personally believe, and the rest of the team believes, that it's the best thing for the IoT community. Being able to openly collaborate with other people and other solutions to create something robust for the whole Internet of Things is something that is really important. And open source allows us to do that. There's a wealth of knowledge and a wealth of experience that by being closed source, we won't see. And by opening that, we can encourage collaboration. We believe that proprietary development can stifle innovation. Keeping things closed source and proprietary generally just kind of leads to a lock-in scenario. And it's hard to actually integrate with other systems. So, like I said, keeping it open enables collaboration and enables a lot of knowledge sharing, which we'll need going forward. It also kind of provides a building blocks approach to system creation. So instead of buying a shrink-wrap sensor management solution, you can build your own, collaborate with others to improve it, and you could also keep it open source. And that's something that's really powerful. And it's also really fun to just open source stuff, collaborate with people, and solve a really big problem all together. So the Zetta architecture. The fun stuff, technology. This is what a typical Zetta topology looks like. And it's a whole lot, and I'm going to step through it kind of slowly and carefully. So at the very bottom, we have devices. And those devices have just the regular firmware that they would have to communicate with a protocol. And that's something that's really important to us because we're web API guys, we're not firmware guys. So we want the people that know how to write the firmware to be able to keep doing that because they have expertise that we don't have. So we try and let them write firmware in an unopinionated way. These lines represent individual protocols that these devices could be speaking within the topology itself. And if you look at the cube, it's got hub written on it. This is typically a hardware platform like a BeagleBone Black or a Raspberry Pi or an Intel Edison, if you're familiar. And it's just a small computer that's capable of running Node.js and speaking these individual protocols to these devices. Inside, we actually have a little Zetta server. So it's just a really lightweight piece of software that runs on the hub and will talk to these devices and create APIs. From here, we actually expose an API on the hub. There's a web API directly on the hub that you can hit from your local network and create change within the platform locally. But that's not great for all use cases. So we actually have also developed a tunneling protocol that will allow us to connect to the cloud in a secure way and proxy HTTP calls. And I'll go over the tunneling protocol in a little bit. Up here in the cloud, we actually, we have a data store, so you can put data into a storage mechanism. And on top of that, we actually expose another API that will say, this is the current Zetta server deployed in the cloud. And it can be deployed anywhere that runs Node.js. We've tested it on AWS, Heroku, Windows Azure. Anywhere that can run Node can run Zetta. And we've really stuck to that tenet as much as possible. And then on top, we have Zetta clients. So obviously with an API-first platform, you need something to consume these APIs. So we have a ZettaKit client that will allow you to hand that code off to a mobile developer, like you would hand off a Facebook client or a Twitter client. And at that point, it's just like writing code for those platforms or for another API-based platform. The only distinction is that instead of web-based workflows like look up a location or log in or share a post with a user, it's turn on my lights or turn on my stove or what's the water pressure sensor reading coming from my faucet. So here's kind of a different layer or a view of the different layers. Up top, we obviously have our application layer, and that's a REST API. So like I said before, it's just like interacting with any other kind of API. Next, we have our mediation layer, which has our open source device definitions. And those allow you to speak a bunch of different protocols and model devices in a consistent way so it can get rendered in the API. Next, we have 3 silos. And this is the kind of cool part. With the mediation pattern in IoT, everything can be protocol independent. So there's no difference in this API if the LED that you're modeling that can turn on and off is speaking Bluetooth LE or Zigbee or just, it's attached to a Wi-Fi network using SSDP. So down here, we have a bunch of different ways to communicate, and this can all be on one Zetta server. So you can talk to devices using CoAP. You can say, there's a device-specific protocol that I want to use, or, a future protocol that comes up. And within Zetta, you can coordinate these devices with ease. You can sit down and say, when the light bulb turns on, I don't care what protocol it's speaking, just catch that event and send another message saying, send a push notification to my phone saying light bulb turned on. You can coordinate all of that with ease. So, just a couple architecture notes, stuff I've mentioned, but I'll reiterate. It's a lightweight process. Zetta itself is a lightweight process that lives in multiple places. First, on the edge of the network, inside of a hardware hub, and then in a data center or the cloud. So you don't need to deploy it to the cloud. You can have it just in a data center, hidden from the public, and it's something that you can monitor and still build your large system off of. Zetta will actually mediate all these hardware protocols in the hub. The only requirements are that you can access it in Node.js, which another big benefit of being a part of the Node.js community is that people are really interested in this stuff. So we've actually written a bunch of device definitions already for a number of different protocols, and we haven't had to write that layer once. There are people that have already written stuff to communicate over Zigbee, to communicate over Bluetooth Low Energy, to communicate over SSDP. It doesn't matter. It's really cool stuff. Zetta processes communicate by establishing that secure link between each other using what we call the Z2Z protocol. I'll go over how we implemented that because it's kind of cool in a minute. And Zetta maintains this layered approach, like I just showed, that keeps everything pluggable. You can pull an old light bulb out and put a new light bulb in, and as long as your device definition is good to go, it'll be transparent to a mobile client. So I mentioned this linking protocol where 2 Zettas will talk to each other. And what happens is we have 2 Zettas here. One lives in the cloud, that nice puffy cloud. And the other one is in a home network, probably behind a firewall or it could be a custom configuration. So what happens is Z1 will make an outbound upgrade HTTP request to Z2, and that will establish a WebSocket connection. And if you're familiar with WebSockets, that's just a TCP socket with additional framing on top, made for the web. We actually take that TCP socket and then create a speedy connection using that socket, just that TCP socket. And Speedy is a predecessor protocol to HTTP2. And it supports using one socket to multiplex and demultiplex multiple HTTP requests going up and down a single pipe. And then after that, it's just a matter of proxying HTTP calls. So Zetta 2 has no knowledge of what devices are connected to Zetta 1 or what devices could be connected to other Zettas. It just has knowledge that it's connected to Zetta 1. And whenever a request for Zetta 1's devices or to do something to Zetta 1's devices come in, it just sends that whole request down that Speedy connection for the API server on Zetta 1 to interpret and take action and send a response back. So I've mentioned a little bit about device definitions. So we call them drivers. And these are just node modules that you can publish on NPM that are just little snippets of code that define what a device can do and how to communicate it over a specific protocol. And we chose a simplistic state machine model. So if you have, for example, an LED over here, it's got two states, off and on. It starts in the off state, and to turn on, you have to go through the turn on transition, and to turn off, you have to go through the turn off transition. And that allows us to express stuff consistently within the API so people can actually understand it and use it. It's really expressive and it's really cool. I'll be able to hop into the JSON and just show you exactly what it looks like. And now it's time for the demo. So let's see all of this stuff at work. And open up my web browser. So the first thing is, this is an API running on Heroku. So if you see it, it's zettacloud2.herokuapp.com. Zetta runs on Heroku and can do this peering connection really easily on Heroku. We use a specific style of API known as hypermedia. So essentially, it takes all the good stuff about HTML and allows us to apply it to API design. Linking, state machines, all that great stuff, which is perfect for the Internet of Things. So the first thing we'll see is, we have a class of root. That's the root of our API. That's what we're going to see when we enter any kind of API. Next up, we have a bunch of links. So you can actually connect a bunch of Zettas together and just crawl through the links to figure out what devices you have on each Zetta. So we obviously have a link back to ourselves, so we can always go back to ourselves if necessary. And then we have our cloud server link, which won't have any devices on it. Next, we'll have a Detroit link, which will have our peered connection. So the server we have living in Detroit right now is connected to this server, and we'll be able to access it and actually manipulate these devices. And then at the bottom is peer management. So another important thing to know, you can do all of this stuff in code, but you can also do all of this stuff over API. We really went crazy with the API first paradigm. So if I hop into my Detroit server, we still have all the links and the actions and stuff. Here is a list of sub-entities. So these are devices that are in Detroit right now. We have our system, so if we ever wanted to restart our system, we could. Shouldn't do that for the demo right now, but we could. Here's a display screen. So we have a touch screen that I'll show you with video in a second that allows us to actually interact with a touch screen, so we can print text. So let me open this up. Do a quick refresh. Make sure that I'm not working okay. So before we go any farther in the API, I'll show you our demo setup. So this is actually a live webcam feed of a robot arm in Detroit, Michigan. First, we have an Arduino that's connected to this robot arm, and this does motor control, and it talks UDP, just a proprietary UDP protocol. Up here, we have an Arduino that will stream sensor values, sound, and light, so we could probably tell that it might be night in Detroit, and it should be really quiet, because nobody should be in our office at, I forget what time it is, but it's like 2 in the morning. Over here, we actually have some environmental sensors, so temperature, air pressure, and humidity, and all of these will be streaming in real time. Over here, obviously, we have our touch screen. So that's our screen that we'll actually write some text to that we can see update in real time. And then at the top here is this hub server that I keep talking about. This is a BeagleBone Black. It's capable of running Node.js, and that's where the API will actually live. None of these things are running JavaScript, but they're all connected and mediated with this device up here. So obviously we crawled our API, and that's fun and makes for a good talking point in a demo, but for development that can be a pain, especially if you use curl or other API tooling to develop APIs. So with this, I'll give this a quick refresh as well. This is the Zetta browser. So this is a static web app that is literally just an API console. We're not doing anything special or proprietary. We're subscribing to WebSocket links that get featured in the API response, and we're rendering the API response with just a little bit of Chrome over the top. So up here, we have our display screen, and we have all our devices connected. At the very top here, we can see sensor data streaming over the API, so over the WebSockets. I think they're down now. That's okay. So I will do this. Oh, it's also nice and responsive, so you can develop with a mobile phone if you want. Move this over. Change. Give it a couple seconds because the speed of light, but right there, we just hit an HTTP API that hit a server in Heroku, probably allocated on the west coast of the United States, which sent a HTTP request down a speedy server, or down a speedy connection to a server that lives on a BeagleBone Black in Detroit, which sent a message over proprietary protocol suite, I think it was Fermata or something, down the serial USB connection to this Arduino. Arduino interpreted those bits and wrote text to the screen. So there's that, and then we can also move our robot arm. So give that a couple minutes. I'm going to open up the claw. This one takes a little bit longer. So we can open up our claw. We've had people try and build things with it and all that stuff, but it's usually kind of hard to do because this robot arm isn't very robust. But it's all over APIs. I'm moving all this stuff in real time, and you should be able to see it go crazy and do some movements. And that is how we've applied all this research over the past year, and it's worked really well for us. We've done stuff with Zigbee, Bluetooth Low Energy, SSDP, and all sorts of different protocols for maker devices. But we've also developed device definitions for consumer devices. So if you have a Philips Hue or a Sonos wireless hi-fi system, you can throw that into Zetta and actually get your, if the moisture goes through the roof, you have your Sonos play your favorite song for when it's raining. You can do that. You can create those coordinations. So, yeah. So here's some additional resources if you want to learn more about Zetta. I'll be here to hang out after the fact. But the first one is Zetta GitHub. We've worked really, really hard to make sure everything we do is open source. It's either open source on one of the developers' GitHub pages, or it's open source up on the Zetta GitHub page. So if you're interested in seeing how we implemented stuff in core, if you just want to learn a little bit more about Node.js, check out our repo and just start reading our code, giving us feedback. We have a self-guided workshop, or a workshop that I usually teach for people, building a home security system using Zetta, and it illustrates all of these features in kind of a quick, elegant way. And all that code lives right there. So you can actually just look through that code, and we'll look through it in a second, and see what the JavaScript looks like. Next is the Zetta mailing list. And that is just our Google group to, if you have questions, if you want to answer questions, if you want to collaborate, that's where you would go. And we've actually been working on an IoT Craft mailing list as well. So if you're interested in IoT, or you're a current practitioner, we invite you to join us over there as well. And you can, ask questions, collaborate, and all that great stuff. And then my personal email is matt@apigee.com. So if you ever have any other kinds of questions that you don't think would fit the first two things and you just want to shoot me an email, please do. So we will actually look at the security system stuff. So just to look at a little bit of code, I'll zoom this in actually. This is the Zetta security system. So what we have is a hub that can have a couple pins on it, like Arduino pins. And what you'll do is hook up a microphone to take sound readings, hook up an LED to turn on and off, and hook up a buzzer to turn on and off so you can make noise. We also include a Bluetooth Low Energy light blue beam, which is a microcontroller that speaks Bluetooth Low Energy that has a couple sensors on it that you can stream off. And just to create an API server is this amount of code. So we've kind of followed some of the design patterns in JavaScript that Express follows because we want it to be that easy to make an IoT API. So we do all our require statements here where we require in device definitions, state machines, other kind of server extensions if you want to do API management stuff. And then we just call Zetta as a function, the Zetta variable or library. And then we just do use for everything. And what use will do is take that device definition. Can everybody see that okay? It's kind of weird. Okay. So it takes those device definitions and those app definitions, reads them, allows Zetta to talk that external protocol, but takes those state machines and creates an API from them. If we wanted to look at our LED, this is what this would look like. So we do some requires for external libraries again. We have one specifically for making pins high or low called MRAA.js. This is specifically built for the Intel Edison. And we do some inheritance because we do some goofy stuff that will allow us to give uniqueness traits and stuff to a device in an API. But down here is where all the good stuff happens, where the state machine stuff happens. So you give devices a type so we can write queries against them. You give them an initial starting state. You can give it a human readable name so you can locate it in an API easier. And then it's really just as simple as these 4 lines for configuring a state machine. When off, we allow turn on. When on, we allow turn off. Then, after that, we take these transition keys and we map them to actual executable JavaScript. And then down here, all we do is write 1 to the pin if we want to turn it on, and write 0 to the pin if we want to turn it off. So I don't know if there are any questions, but I'd like to thank everybody for listening to me talk about Zetta. And I will be here after to hang out, and if you have any questions, please let me know. I don't know, are there any questions? I did a lot real quick, so.
時間が若干ありますので、もしご質問があれば。大丈夫ですか？よろしいですか
？Do you have any plan to provide a smartphone SDK iOS tracking?
So do we have plans to provide a smart home SDK? So I don't quite know what you mean by that, but we do have, we're working on polishing off our Zetta SDK libraries. And then from there, you can build in JavaScript your smart home, or look up somebody that has built the smart home platform specifically for some devices on Zetta, and then use Zetta Kit to actually build the mobile app. That's what you mean. Yeah, it's a very much a building blocks approach. So we try and stay obviously protocol agnostic, but solution agnostic as well. So there could be somebody that thinks the perfect smart home is Belkin Wemo, Philips Hue, and the Sonos, but somebody else might think it's a different hi-fi system, lights from GE Corky, and a Panasonic TV. And we allow people to be flexible like that. Sure. So, you'd also like to check out our open source webpage. This is zettajs.org. So this is where you can actually go to learn a ton about the platform. We're still perfecting everything right now. But like I said, we're trying to grow our community and our documentation base. Right now, it's got just a little bit of information on this page about how to get started, and some code snippets and some compatibility things, like where you can actually run Zetta, where we've tested it. And defines what kind of APIs we have for stuff. The most interesting part right now is our projects guides, where we actually have ways to get started with Zetta. So right here is the Hello World project, and that's written by my colleague Adam, who's actually in the audience. We'll be here to talk about Zetta as well. You'll actually be able to get started without any devices and just learn how to use the APIs and learn how to use the JavaScript. We have some simulated devices that you can just see sensor values streaming that are obviously mock, and a mock LED. Next up, we actually want people to share projects too. So if you build a really cool robot or your home automation platform, write up a project for us. We will put it on our website gladly so you can show other people how to use Zetta. Here's our home security with the Intel Edison. So this is the docs behind it, so you don't have to just follow along with the code. We have nice little graphs and animations and stuff. And then we actually have another version of the home security workshop with the BeagleBone Black. So there's that. Then we're working through everything else. But we have guides on how to create, device drivers, other interfaces. We have a concept known as scouting, where if you're speaking a wireless protocol, you have something that functions like radar to go out, locate devices, figure out some config information about them, and actually make sure that Zetta knows that they're present. And it's good so you can wait for something to create a connection or system resources to be online. Tour of the Zetta browser. We give you a quick guide to actually write stuff with proprietary consumer devices, so our Hue driver and all that great stuff. Device API tour. Let's dig. Actually, we should probably dig a little bit more into the device API. So if we take a quick look at our screen, this is actually what a full device API would look like in JSON. We use a spec called Siren at sirenspec.org as a way to format our API. And Siren defines a couple properties. The first one is class, so you know what the actual API response represents. The next is properties, which is just a key value bucket of specific things that are in the API. Next are actions, which in hypermedia represent state transitions. And the last thing are links, which we went over, which are just links to other important resources that are related to this object somehow. So if we take a look in properties, we have a state of ready, and that is an important key to take note of when you're actually interacting with an API, because that string key will determine what transitions are available. If we remember, we looked at the device driver. And while it's ready, we only allow change, which allows us to update that screen. So I wrote some text in there, and that's how we do it. And everything is really descriptive, so there's no inference about anything. We found that using other hypermedia types or other API design methodologies, it can be kind of hard to figure out what exactly you need to send down. We don't know if there's extra parameters. We don't know if there's no parameters. We don't know, what could be the HTTP verbs we even want to use. But for this, it allows us to be extra descriptive, give our transition a name, an HTTP verb, an exact link to send that to, and then parameters that are necessary. And we found that this is the best way to go about stuff because it does add overhead, but at this point, it's just HTTP. And we've gotten really good at optimizing HTTP through other methods where extra content in the API payload should not be that big of a deal. So, yes. Down here, we actually have some WebSocket links for sensors, so I mentioned that. When you saw the colors flash on the API browser, that's because we actually publish tons and tons of events up WebSockets for people to catch and interpret, and state is one of those things. So not only can you stream sensor values, you can stream states of devices and read what's happening to them in real time over the API. And just like we provide HTTP links that people can crawl to, we provide WebSocket links that they can subscribe to. And if you use a utility like WSCat or a WebSocket, other WebSocket command line utilities, all you need to do is set up a connection with this exact URL. There's no proprietary protocol or anything. You just need the link, and it will start publishing events to you in real time. So if I do click on message, WSCat-C. So that is connected, and I should be able to refresh. And this property will publish up the WebSocket. So we can actually pull these values from the WebSocket. We add some extra data in there for collection purposes. So we have a topic string, and what that represents is the type of device that published this event, the UUID of the exact device, and then the parameter that it published, so message, timestamp, so that's the Unix text directly from the gateway. And then the last thing is data, which is just the message that I passed up that WebSocket. So. Is there any other questions? Anything else that you're curious about that I could show off that maybe I didn't mention?
Yeah. If I were a builder of the system, do we have any prototype of APIs such as this prototype or microphone type?
Yeah, we're building all of those out right now. So we definitely have some prototypes for what a microphone would look like, what a solar sensor would look like. They're generally more simple state machines, and I think I actually could probably pull that code up right now. If we do. So this is actually a microphone device driver, a device definition. And I just open it up like so. And really all it is setting, we don't recommend you set the throttle rate of how much you sample data off a sensor in JavaScript, but you can. But all it really is setting a property in JavaScript up here. So we have the volume property where it is, it's right here. And we do some setter magic in JavaScript to catch that, the property was actually set. And we publish it up the WebSocket. And the way we define that in the driver is just monitor. So there's no state machine semantics in this because there's nothing to do with the sensor. It's just going to read data. So, did I answer your question?
Yeah. For my progress, it's okay, but for like number, moving up.
Mm-hmm.
Device vendor or machine vendor need to define the API by ourselves or whatever.
So would it be like a custom device with a proprietary protocol, or would it be so there's typically two concerns. One is the modeling of the device, like how you want to stay within the state machine, how it moves. And the other one is how you actually want to send messages to the device itself. Typically, what we've done is we've actually had compound devices with sensors and actuators on them. And usually these sensors just report back the state of the device in terms of like what position stuff could be in. And we use the state machine to say like, hey, we want to move it this. And then if you need more control over it, where you say you want to move one motor 10 degrees, you would define an input for that transition that says, I'm looking for a degrees parameter, so I know how much to move the motor. And it's not very apparent in our robot arm because we use a different kind of motor than like a servo or something that can be controlled easily. So we just say, you know, move it for 3 seconds. It's an arbitrary value. It'll fire off the motor and stuff. Any other questions?
大丈夫でしょう。ではちょっと10分程度早めですけれども、これでセッションを終わりたいと思います。Thank you.